This last problem in the energy packet. It's an old AP free response problem. It's actually from 1995, but there's some bits about how this problem was written that are not so good, and so you know they're better at writing the problems. Oh my gosh, this is 25 years ago. Holy cow! That's 5 years after I graduated high school. Anyway, they're better at writing problems now. There's a couple things they did here that are really annoying. So we'll kind of I want to talk through this with you rather than you just like looking up the solution online, because it's not going to be very great. So here we go. So here I have a potential energy versus position graph. They tell me a particle of mass m moves in a conservative force field described by the potential energy function that U is A times the quantity R over B plus B over R, where A and B are positive constants, R is infinite origin. Here is the graph of that function. So that is the graph that goes with that equation. In terms of the constants A and B, can you find the position R naught at which potential energy is a minimum? You say, yeah, look, sure enough, R naught, I can see that is where U is at its minimum value, and they're calling that U naught. That notation wouldn't be so bad if this was like the starting position for the particle later on in the problem. It's not. It's the ending position for a calculation later on. So it's really super annoying that they called that naught. We'll deal with that when the time comes. But anyway, here we go. In terms of A and B, find that position. And so you say, well, I'm going to use this equation, right? And what you need to do is find R naught. You say, well, I can do that because that's the minimum value. Here's the function. I just need to find the R value that makes this minimized. Like, I remember how to find the minimum value of a function. This is something I learned in calc class, or perhaps in AP Physics. You might have learned this earlier in this course if you hadn't gotten to that in your math class yet. That is fine. Okay, we can do that. So here we go. I'm going to kind of go back and forth between doing my work here and doing my work here. So for part A here, okay, we want to find U minimum. All right. And so what I'm going to do is I'm going to take the derivative with respect to R to find the value of R that makes up the minimum, and then I'm going to set that equal to 0. That is the trick. So 0 is going to be the derivative of that function, A times R over B plus B over R. All right, when I take the derivative, let me just distribute that A right away, okay? That'll make it a little bit easier in my brain. So I'm taking the derivative of A over B times R plus AB times 1 over R. Okay, that's the way I'm going to think about it, like that. All right, I know I'm just tidying it up, but it helps me. So the derivative of AB times R, that's just A over B, right? A over B times R is AB. That's the slope, right? And now here, this is AB times R to the minus 1. Well, derivative of R to the minus 1 would be minus 1 times R to the negative 2 power, right? And that AB is coming along for the ride there. That's what I would get. I could write that a little bit tidier as A over B minus AB over R squared, right? So that I am setting equal to 0, right, to find the minimum. Now you just need to solve for the R that makes this minimize. You're like, okay, all right, well, rearrange this, move the AB over R squared to the other side. AB over R squared is A over B, right? And then you say, hey, look, do you notice that both terms have an A in it? I can divide through by A. Bam, bam. Let's see, let's divide by B. I'm going to end up with R squared is B squared when I rearrange that. And so R is B. Okay, and we remember, yeah, there we go. So R is B is our answer. Okay, that is the value of R that makes that minimum. Hey, by the way, that's R naught. So technically, as soon as I set this to 0, I was solving for R naught, actually. Use their notation. Okay, so R naught is B. Okay, right, as soon as I set to 0, I'm finding the minimum, so that R would be R naught. Okay, let's go to part B. I'm sorry, that was AI. Now we're going to go to AII. All right. AII, find that minimum potential energy U naught. So I just want to find the U when R is equal to R naught. So I'm going to take that U function. U is A times, let me do that nice form that I came up with there. A over B times R plus B times 1 over R. Okay. And what I want to do is I want to go ahead and plug in R naught. Well, R is R naught, R is B. So that U minimum, which they're calling U naught, is going to be A over B times B plus B times 1 over B. And you say, well, if I do that, right, the B on the bottom, B on the top, they're going to cancel out, right? See that A there? I left that out here. Sorry, there's an A here too. But you can see these B's are going to cancel and these B's are going to cancel. So I'm going to get A plus A. I'm going to get 2A. So U naught is 2A. Okay, that's the first part of the problem. Okay, now we're ready to go to part B. Part B says they would like us to sketch the force as a function of R on the graph here, considering a force directed away from the origin to be positive and towards the origin to be negative. You say, sure enough, a force, here's the origin, away from the origin is the positive direction. Yeah, I know. Who would have graphed it any differently? But anyway, there's emphasizing. So, hey, let's do a graph of the force. So when I want to graph force from my UR graph, it makes sense. I remember that force, I'm going to go ahead and I'm going to write on this one, okay, because they gave me these axes to use. I know that force is negative dUdr, okay, that force that's responsible for that potential energy function. And so I'm just looking at the slope of this. I want to graph the slope, the derivative of this, but then flip the sign, negative the slope. So the first thing is find the zeros. You say, hey, when is the slope of the zero? Well, it's at R naught. So that is going to have a force. The derivative is zero. The slope of this is zero. So that'll be the zero right there. That's when it crosses the axis. I know that all through here, my slope is negative, decreasing, flattening out, getting a smaller size slope, a smaller magnitude slope, but a really big negative slope heading to zero. So I'm going to have, and this is like, looks like maybe even like asymptotic, doesn't it? So I'm going to have an asymptotic, it's a negative slope, but I flip the sign on the slope to get the force. It's a big positive value. It's going to be decreasing and crossing the axis there. Here I've got slopes that are positive, and so my force should be negative. So I'll be down below the axis. I'm going to cross the axis at R naught. And you notice how this is pretty dang straight? Now, if I had some numbers here, I could actually calculate what that slope was that I was approaching and put some numbers here. They didn't give me any, so I can't actually assign any values. But I know this has got to head towards a straight line, so it's a constant slope. So this has got to head to a constant value for force. A constant positive slope will be a constant negative force. So this graph is going to start kind of asymptotic, cross the axis at R naught, and then approach some final horizontal value, start to flatten out there. Okay, so that's the shape of graph I should get. Like I said, I can't set specific values because I don't have any numbers on this axis, but that's the shape I should get. All right. Part C. This particle is released from rest at half of R naught. Okay, now, we're going to let this thing go from here, from R naught over 2. I'm going to let go of it there, right? Okay, and its potential energy will be this much then. Anyway, I'm going to let go from there at rest. So at this point, all the energy is in potential energy to start with. I know that it's going to get shoved to the right because it's a negative slope, so it's a positive force. We'll push this particle to the right when I let go. What I want to know is what's the speed of the particle when it gets to R naught, when it gets to here. So we're going from here to here. Look, see, we're ending at R naught. That's annoying. I wish they hadn't done that notation. We're starting at R naught over 2, right? We're starting here and going to there. Now, R naught we know happens to be B, so this is B over 2 is the position we're starting at. Okay, they want to know in terms of U naught and M, determine the speed of the particle when it gets to R equals R naught. So you say to yourself, well, okay, I want some more blank paper to work with here. So grabbing that blank paper, giving some space to work. Like I said, on the real AP problem, you will have plenty of space to work. I jammed everything onto one sheet of paper, so I wouldn't have to print out too much paper. All right, so sorry about that. But we got the space here for doing part C. All right. Okay, part C. Okay, so we want to know the speed when it's at R is R naught. Okay, now if it were me, I would say, hey, look, I'm going to go. My object's going to start at rest at R naught over 2, and it's going to end at R naught. And so I'm trying to find the velocity at R naught. I'm going to do an energy calculation. I'm going to do a little sigma W is delta K plus delta U. I'm assuming the only force is this conservative force field that's responsible for the potential energy function. And so there's going to be no work. I'm going to have my K, let's say the K at R naught, okay, minus the K at R naught over 2, okay, plus the U at R naught, which we'll fix that in a second, minus the U at R naught over 2. Okay. All right. Now, we know something here is going to cancel out, and that is we know that we're starting from rest. So when we're here at R naught over 2, this kinetic energy is going to be 0. I'm trying to find the velocity when I get to R naught. So I'm trying to find the velocity is going to be in that kinetic energy equation. So I'm going to go ahead and substitute that in. It's important to write the potential energy function showing only the non-zero terms. All right, fine. It's going to be my kinetic energy at R naught plus my U at R naught. Now, you know, the U at R naught, that's what they just called U naught, isn't it? So I'm going to write that there. That's our final potential energy, not the initial. It's annoying, their notation. And then minus the U at R naught over 2. Yeah, that's my initial, but I can't use a naught. I could use a little I for it. That's okay. That's okay. We'll just say at R naught over 2. We know what that means. That's a subscript describing the U. Okay. Okay. So I can show my energy terms here. Here's all the non-zero terms. This is something I tell you to always write. The work energy theorem showing only the non-zero terms. Okay. We're trying to find the velocity. That's hidden in the kinetic energy equation. So I'm going to use the kinetic energy equation 1/2 m, that V that we're trying to find, okay, which is going to be the V at R naught. They would probably like you to call that V naught to follow their notation here, but I find that irritating. It's just the V we're trying to find squared. Okay, now U naught, our answer, they tell us they want the answer in terms of U naught and M. So I'm going to leave this U naught alone. Minus the U at R naught over 2. So I need to find that U at R naught over 2. So what I'm going to do is I'm going to go back to that U equation. I'm going to do this work over to the side here. I'm going to say I know that U is A. Yeah. All right, fine. R over B plus B over R. Yeah. And so the U is, again, A over B times R plus AB times 1 over R. Okay. I just like that notation with the variable isolated out from its coefficients. Now what I'm doing is, we remember that R naught came out to be B, and we're supposed to be looking at R naught over 2. That'll just be B over 2. So I'm going to plug B over 2 in for R. Okay. So my U at R naught over 2, right, is going to be equal to A over B times B over 2, right? Plus AB times 1 over B over 2, okay? If I do this, you say, oh, some cool stuff's going to happen here. You say, this be brink, and this be brink, right? And what I'm going to have then is that my U at R naught over 2 is going to be, that's A over 2, or half A, plus, and now this is A over 1/2, 1 over 2, right? We divide by half, multiply by 2, so this is just going to be 2a. That's equal to 2a and half a, that's 5/2 a. Is that u at r naught over 2. Okay. Now, so I could put the 5/2 a in there for r naught, u at r naught over 2, but I want my answer in terms of u naught, and I already know a relationship here. I know that u naught is 2a. Can I rewrite this in terms of u naught, in terms of 2a? In other words, can I factor a 2a out? Because that would be like u naught, right? What would I have to multiply 2a by to get 5/2 a? I'd have to multiply that by 5/4. Do you see that? 5/4 times 2a would be 5/2 a. So u at r naught over 2, that's 5/4 times u naught, because u naught was 2a. So that's what I'm going to put in there for u naught over 2. All right, because they wanted it in terms of that. All right, so this is going to be 5/4 u naught. All right, okay, from here on out, it's going to be a little bit tidier. Half mv squared. U naught minus 5/4 u naught is minus 1/4 u naught. Okay, and now I got an equation. It's got v and just m and u naught, which is what I wanted. That was there. So rearranging. Okay, I'm just going to move the 1/4 u naught to the other side. I'm going to multiply through by 2 and divide by m. Is it okay if we do all the algebra at once? Yeah, that's fine. Okay, I'll do almost all the algebra at once. V squared is going to be equal to a 4th u naught times 2 over 1, right? So it's going to be, right? Right. It's going to be u naught over 2 m. Yeah, so the v will be the root of u naught over 2m. There we go. Whew. Okay, that's what we're trying to find. Okay, that was a lot of algebra for part C of this problem. Yeah, and that was, it's made so frustrating because they decided to call the initial one naught. And it makes me not want to use their notation, but I'm stuck with it. And so that's really aggravating. Okay, but that's what I ended up doing. Okay, so just realize the naughts are the finals and the r naught over 2s are the initials. Okay, okay, there. Okay, so that is part C. Okay, part D. I'm also not wild about how they wrote part D. Part D says, write the equation or equations that can be used to determine where, if ever, the particle will again come to rest. It's not necessary to solve for this position. So you're saying, okay, well, I just wrote an equation here, right? Kinetic energy, here's the velocity. I'm trying to write an equation to determine when the velocity will be 0. So assuming I'm starting, again, notice that all of this, C, D, E, this is under the heading, the particles released from rest at r is r naught over 2. So we're working from that information, okay? So if I let it go from here, how fast, is there some point where the speed would again be 0? You say, well, yeah. As it goes down here, it's losing potential energy, gaining kinetic, but then it would have all this speed when it gets there. It would continue up the other side here. Now it'd be gaining potential back again, losing kinetic. There'll be a point where the potential energy, and I don't know what the value is. I mean, who knows what that is? We don't have to solve for it, thank God. But the point is, there's a point over here where that potential energy would be back to the same as it started. I wouldn't have any kinetic energy left. That's the spot we're talking about. How would I solve for that spot? Well, I just wrote an equation for velocity here. Here, if instead of, this is just my final u, final, yeah, here's my final minus initial, okay? So I'm gonna do the same setup. It's gonna be, except now I'm trying to let it go from here and have it end here, right? So sigma w, I'm just gonna start from fresh. Delta k plus delta u, okay? And it's gonna be, my final kinetic energy would be 1/2 m v squared. Actually, let me write it out. Let me write out the big terms first. My final kinetic energy, yeah. I want that, sure, fine. Minus my kinetic energy at R naught over 2, because that's where I'm releasing it from, plus my U final, whatever that is. I'm just going to write it as U final, fine, whatever. Yeah, my U at my final position, which they didn't give a name, so I don't know. I don't know what to call this. Let's just say the final position, okay? Where the potential energy is the same as at the start, minus my original potential energy. All right. Yeah. My original here, which is the U at R naught over 2. Okay. Now, if I do that, I realize, wait a minute. I'm trying to find a spot where it comes to rest, and I'm starting with it at rest. So the kinetic energies at the start and the end are both 0, right? So from this, I would get an equation for my final U, right, minus my initial, and I'm starting at the U at R naught over 2. Now the U at R naught over 2, now the point is, at this point, so you could hypothetically rearrange this and say my U final is going to equal my U at R naught over 2, right? If they add to 0. And I could start like putting in expressions like the UF, the U, that final U is going to be using my equation, right? This A times R over B plus B over R business, right? Where this R, this is the position I'm trying to find. This is my final position, right? Okay. Would be equal on the other side to the U at R naught over 2. Well, you know what? The U at R naught over 2, we figured it out before. It's 5/4 U naught. And technically, U naught, we figured out was 2A. So this is 5/4 times 2A. You know what I mean? We could continue on with this. 5/4 times U naught, right? Bringing this down from here. Okay, and from the other page, we know that that's 5/4 times 2A, right? And so that would be, what is this, 10/4, 5/2 A. Okay, and so 5/2 A is equal to this, and so that's the expression that I have to solve. Let's go ahead and move that A to the other side. So I'd have like R over B plus B over R equals, now I'd have 5/2 A squared. And I have this expression that's got 2 R's that I have to solve somehow. Yada, 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 yada. Point is, where do you stop? Right? You know what I mean? They say they want, and this looks yucky, to solve, but the point is they say, just write the equation we're going to be used to solve when we come to rest. It's not necessary to solve for this position. It's like, well, where am I supposed to stop? The official AP scoring guide says, really, that's all they want you to show. That you would set the 2 potential energies equal to each other, because those are equations in terms of position, and you're trying to solve for position, and that's as far as you actually need to go. All right, but this is the way it would shake out after that as you start trying to solve for R, and you would just solve this expression. Yep. I'm going to be honest with you. When I look at this, how would I mathematically solve for R here? That's really awkward. Glad I don't have to do it. Okay. Oh, I'd multiply through all terms by R, and that would give me an R squared term, a constant term, in R to the first power. It'd be a quadratic I would solve for R. That's what I would do. I'd multiply through by R, and then I get a quadratic to solve. Okay, but anyway, we don't have to do that. We're done with part D. Okay, which takes us to part E, which says briefly and qualitatively describe the motion of the particle over a long period of time. That goes like this. I'm just going to give it verbally to you, if that's okay. Well, heck, we'll do it. What this particle is going to do, I'm going to start it here at R naught over 2. You say the slope is negative of the potential energy, so the force is in the positive. It's going to get pushed. It's going to accelerate to the right until it gets to R naught. At that point, the force is decreasing because the slope is decreasing. It gets to 0 there, but it's not going to stop there. It's been picking up all this speed. It's been pushed. It's been accelerated all the way to there. So it's going to overshoot that equilibrium position. When it comes over here, now the force is negative because the slope is positive. The force is negative. It's going to push against the motion and slow it down, bring it to a speed of 0 here. But it's not going to stop because the slope is still positive. It's still a negative force. It's going to push it back. And so this thing's going to oscillate back and forth and back and so it's going to oscillate back and forth here, right? So it's oscillating around R equals R naught, okay, is what I might say. Okay, and it's going to go from R naught over 2 up to, and again, we never found a value for this position, so it makes it awkward to talk about, but it's going to oscillate back and forth between there and there. It doesn't have any more energy. It can't get past this point. It's just going to get there, but the force is negative. It's going to push it back, right? Same thing. It can't get past that point. It's going to come to rest there. It's bound, right, with the maximum energy here of this, the U at R naught over 2, which was 5 force U naught. Anyway, so that's where that is. It's 5 force U naught. That's the idea. It's going to oscillate back and forth, back and forth. Okay. The AP scoring guide for this part was really awkward. It was like saying it's going to oscillate was a point, and then explaining that it's because of conservation of energy is why it's stuck there. They never, in the question, tell you that they want you to talk about the why or justify. So this was a poorly written problem. Again, not real happy with it. But there you have it. Okay. I feel like this problem was a little ugly. I think the writing on it could use some help. But the basics of understanding what's happening here, being able to work with a U as a function of our function to find the force function, drawing the graph, answering some questions about the relationships of energies, kinetic and potential for this, those are all good, solid things you should be able to do. All right, so that's that free response problem.